So imagine your CFO just walking right into your office, right?
Oh boy, that's never good.
No, it's really not. And they're holding an AWS bill for like $50,000, and it is purely, entirely accidental NAT gateway data transfer charges.
I mean, I have seen that exact scenario actually play out in real life.
Right, because the developers were moving fast.
Yeah.
They were pulling a ton of data from S3, and just nobody realized the traffic was routing over the public internet instead of through a gateway endpoint.
Yeah, and that is exactly what happens when your agility sort of outpaces your architecture.
Exactly. And that's really why today we're tearing apart the SAP-C02, the AWS Certified Solutions Architect Professional exam. Because at this level, for you listening, you aren't just building things that technically work. You are building things that have to survive the brutal reality of enterprise constraints.
Right. It's the difference between a simple proof of concept and actual production at scale. At the professional level, I mean, the cloud isn't a playground anymore. It's a total minefield of trade-offs.
100%.
You are constantly balancing strict cost thresholds, unforgiving latency bounds, and honestly, the absolute silent killer of all IT departments, which is operational overhead.
Oh, the overhead is what gets you.
It really is. Like a solution that technically functions but requires, say, 3 engineers to maintain it every single weekend. That is not a well-architected solution.
No, it's a liability.
Yeah.
And that brings us to the core mission of this deep dive today. We are stepping into the ring against, honestly, the biggest adversary in cloud architecture today, which is the public forum hive mind.
The hive mind is so dangerous.
It really is. You go on Reddit, you hit Stack Overflow, and you see these community discussions where people just panic vote for whatever legacy tool they used at their last job, right? Or they string together these incredibly fragile, over-engineered architectures.
Yeah, the hive mind has this really dangerous tendency to just default to heavy EC2-based solutions for literally everything.
Yep.
Or they just completely misunderstand the native abstractions that AWS has spent, the last decade building.
Exactly. And the SAP-C02 is explicitly designed to test whether you can spot the elegant, managed solution hidden among some very plausible-sounding distractions.
Right, because the distractors on this exam, they aren't necessarily broken. I mean, they compile, they route traffic, they just fail to meet the specific constraints of the scenario.
They fail the business requirements, yeah.
Yeah.
So let's get straight into the architecture. I want to start by laying the absolute foundational plumbing of any enterprise environment, which is the network.
Let's do it.
So we've got a scenario here that perfectly illustrates this sort of tension between central control and developer autonomy. Picture this. A company is operating under AWS organizations. The central infrastructure team has a dedicated, locked-down AWS account.
Okay, pretty standard.
Right. And inside that account, they have a single VPC. It is their absolute mandate to manage this network. They control the IP address space, the routing tables, the subnets, the internet gateway.
They own the perimeter.
Exactly. Now, you have dozens of individual application accounts belonging to different product teams. Those teams need to deploy their resources, their EC2 instances, RDS clusters, Lambda functions, into those central subnets. But, and this is the kicker, under no circumstances can those individual app accounts be allowed to modify the network itself.
Right, so it's a classic separation of duties pattern. The network engineers want absolute dominion over the blast radius of routing changes, while the application developers just want an IP address so they can ship their code.
Exactly.
Yeah.
But you read the forums, and the second the hive mind sees the phrase multiple AWS accounts, they just start screaming for AWS Transit Gateway.
Oh, every single time.
Every time. They argue like you've got dozens of accounts. Boom, split up a Transit Gateway, make it a hub, and peer every single app account's VPC to it. So play devil's advocate here. Why isn't Transit Gateway the right call? I mean, I get central visibility, I get deep packet inspection, and I keep the accounts isolated.
Well, because you're arguing for a completely different architecture than what the actual constraints dictate. I mean, Transit Gateway is a phenomenal service, right? It's a massive, highly scalable cloud router. But look closely at the underlying mechanics of what you just suggested.
Okay.
If you use Transit Gateway, you are forcing every single application team to create, manage, and maintain their own VPCs in their own accounts, which you then attach to the hub.
Which violates the central team's mandate. The prompt says the infra team manages a single VPC, and once the resource is deployed there.
Precisely. Transit Gateway is designed to connect multiple discrete VPCs. It is a highway system connecting separate cities. But the business constraint here explicitly dictates there is only one city. There is only one VPC.
Right.
Furthermore, think about the operational overhead and the cost. Transit Gateway charges you an hourly fee for every single VPC attachment, plus a per gigabyte data processing fee for traffic flowing through it.
That adds up fast.
It adds up incredibly fast. You're introducing massive cost and complex BGP routing tables when the developers literally just need to drop an instance into an existing subnet.
So we don't build a massive highway system. We just need to give the developers like the keys to the existing buildings.
That is exactly where AWS Resource Access Manager, or RAM, becomes the optimal solution.
Walk me through that.
So the infrastructure team logs into their central account, goes to AWS RAM, and creates a resource share. They select the specific subnet irons they want to make available, and they share them directly to the AWS organization's OU that contains the application accounts.
Okay, but walk me through the actual developer experience there. Because I've seen teams really struggle with cross-account IMM roles, like trying to assume roles just to launch an instance. It's miserable.
Yeah, that's the beauty of RAM. There is absolutely no complex cross-account role assumption required for the deployment itself. When the application developer logs into their own AWS account and goes to the EC2 console to launch an instance, they will magically see the infrastructure team's subnets available in their drop-down menu.
Wait, right alongside their local subnets.
Right alongside any local subnets. They select it, and AWS provisions the instance.
But the Elastic Network Interface, the ENI that lives in the infrastructure account's VPC, right?
Exactly. The ENI is provisioned in the central VPC, and it draws an IP address from that central CIDR block. But the EC2 compute instance itself, and importantly, the billing for that compute, remains entirely within the developer's application account.
That's so clean. But what about security groups? Like if the infra team controls the network, do they also have to write every single firewall rule for the devs? Because that sounds like a massive ticketing nightmare.
No, and this is a crucial nuance for the exam. While the infrastructure team owns the subnet, the route tables, and the network ACLs, the application team actually owns these security groups.
Oh, really?
Yeah. The security groups are created and managed in the application account and attached to the ENI. This perfectly satisfies the separation of duties. Central IT controls the routing and perimeter boundaries, while developers control the immediate host-level access to their specific applications.
So zero operational overhead for central IT and perfect least privilege networking.
Exactly.
It's elegant.
Yeah.
But let's crank up the difficulty a bit. What happens when the service we need to talk to isn't inside our organization at all?
Third-party integration.
Right. Let's look at the private SaaS consumption scenario. So you need to consume a third-party software as a service application. Let's say it's a specialized, high-throughput machine learning API, and the vendor hosts it inside their own AWS VPC. You need to consume it from your company's VPC. But here are your constraints, and they are brutal. Traffic must absolutely not traverse the public internet. You must adhere to strict least privilege, and absolutely no inbound access to your company VPC is allowed. The communication flow must be strictly unidirectional from you to them.
I mean, these are very standard constraints in highly regulated environments like financial services or healthcare. You just cannot risk data exfiltration over the internet, and you really cannot expose your internal network to a third-party vendor's routing plane.
So I go to the architecture boards, right? And I see two camps. Camp A says, just set up VPC peering. It's free, it's fast, it goes over the AWS backbone. And Camp B says, no, VPC peering is too open. You need an IPsec site-to-site VPN to ensure it's encrypted and locked down.
Yeah, truly.
So let's take Camp A first. If I peer my VPC with the vendor's VPC, I can just write a security group that only allows outbound traffic to their specific IP range. Doesn't that satisfy the constraint?
It technically allows you to communicate, but it drastically fails the architectural intent of the constraints. VPC peering establishes a bidirectional trust relationship at the network layer.
Right.
When you accept a VPC peering connection, you are effectively merging your routing planes. Yes, you can and must try to lock it down with security groups and hyper-specific route table entries. But architecturally, you have opened the capability for bidirectional traffic.
So you're relying entirely on someone like not making a typo in a routing table to prevent the vendor from reaching back into your network.
Exactly. And beyond the security violation, think about the operational nightmare of CIDR block management. VPC peering strictly prohibits overlapping IP spaces.
Oh, that's right.
If your enterprise uses the 10.0.0.0/8 space, and the sauce vendor happens to use that exact same space, you cannot peer those VPCs. You would have to implement this really convoluted private NAT gateway setup, which just introduces massive complexity.
Okay, so peering is out because it's bidirectional and risks IP collisions. What about the VPN camp? If I set up a virtual private gateway on my side, a customer gateway on their side, and establish an IPsec tunnel, I can control exactly what traffic goes through the BGP advertisements.
You can, but you are introducing an immense amount of operational overhead. I mean, you are now managing IPsec tunnel rotation, pre-shared keys, BGP routing propagation, and constantly monitoring tunnel health.
It's a lot of babysitting.
It really is. Not to mention, VPNs have bandwidth limitations per tunnel. You do not deploy a heavy, stateful infrastructure appliance just to hit a REST API endpoint. It's the definition of over-engineering.
All right, so I'm tracked. Peering is too open. VPN is too heavy.
Okay.
How do I consume this service securely over the private backbone?
The native AWS abstraction here is AWS Private Link. Specifically, you deploy an interface VPC endpoint.
Let's really dig into the mechanics of private link, because I think a lot of architects just see it as, like, magic. What is actually happening under the hood when I create that interface endpoint?
So it relies on a foundational AWS service called Hyperplane. The SaaS provider sets up a network load balancer in their VPC and registers it as a private link endpoint service. On your side, the consumer side, you create the interface endpoint.
Okay.
When you do that, AWS drops an elastic network interface directly into your specified subnet. This ENI gets a private IP address drawn directly from your subnet's CIDR block.
Wait, so as far as my applications are concerned, they are just talking to a local IP address inside their own network.
Precisely. They resolve the vendor's DNS name, it points to that local ENI, and the traffic hits it. Behind the scenes, AWS Hyperplane intercepts that traffic, encapsulates it, and securely proxies it across the internal AWS backbone directly to the vendor's network load balancer.
That's wild. And what about our constraints?
It mathematically satisfies every single one of them, because Private Link operates at the service level, basically acting as a TCP proxy. There are no route tables to update. There is absolutely no IP CIDR overlap to worry about because the network planes are never merged.
Right, they never actually touch.
Exactly. And most importantly, Private Link is inherently architecturally unidirectional. The consumer can initiate a connection to the provider, but it is physically impossible for the provider to initiate a connection backward through that hyperplane proxy into the consumer's VPC. You achieve perfect least privilege, zero internet exposure, and zero routing overhead.
That is just flawless. You completely decouple the network topology from the service consumption.
Yeah, it's a game changer.
But let's talk about the glue that holds all this networking together, because none of these private IPs actually matter if the instances don't know how to resolve them. DNS is almost always the silent killer in hybrid enterprise architectures. Like, if DNS fails, the network effectively doesn't exist.
Oh, 100%. It's always DNS.
Always. So here is the hybrid DNS resolution scenario. You've got an on-premises data center connected to AWS via a direct connection.
Yeah.
On the AWS side, you have dozens of VPCs attached to a transit gateway. You're hosting a critical internal application, and you've created a Route 53 private hosted zone for the domain cloud.example.com.
Okay, got the picture.
The constraints are straightforward but demanding. Your on-premises servers need to resolve cloud.example.com. All of your VPCs across the cloud environment also need to resolve it. And you need the highest performance and availability possible with the absolute minimum operational overhead.
Right, and this is where we see the legacy mindset really rear its head on the exam. The shift from on-premises to cloud requires a fundamental rewiring of how you think about infrastructure services.
You aren't kidding. The hive mind trap here is honestly hilarious to me.
Yeah.
You go to the forums, and highly experienced network engineers are suggesting that you deploy a massive fleet of Amazon EC2 instances in a shared services VPC.
Yep.
They want you to install BND or Unbound on these Linux boxes, configure them as conditional forwarders, set up auto-scaling groups, put them behind a network load balancer, and monitor their CPU utilization, literally just to route a DNS query.
It is the absolute definition of lifting and shifting your technical debt. I mean, in an on-premises data center, yes, you stand up a virtual machine to run your DNS forwarder. You have to. But in AWS, managing EC2 instances for core, foundational infrastructure services introduces completely unnecessary points of failure.
Right.
Think about it. What happens when the underlying EC2 hardware degrades? What happens when you need to patch the OS? What happens when there's a zero-day CVE in the bindy software? You are taking on massive operational overhead for a problem AWS has already solved natively.
So we delete the EC2 instances. How do we natively route these queries? Let's start with the cloud side first. How do we ensure all dozens of our VPCs can resolve that private hosted zone?
That part is incredibly simple, but so often overlooked. You don't need any complex forwarding rules within the cloud. You simply associate the Route 53 private hosted zone with every single VPC in your environment.
Wait, it's just an API call to associate the VPC ID with the hosted zone ID?
Exactly. When you do that, you are leveraging the native Amazon-provided DNS, which is that .2 IP address located at the base of every VPC's IPv4 CIDR block.
Ah, the .2 resolver.
Right. This resolver is inherently highly available, it seamlessly scales to massive query volumes, and it requires zero maintenance. Every EC2 instance and every VPC simply queries its local .2 resolver, and because the private hosted zone is associated with that VPC, Route 53 returns the answer immediately.
Okay, that handles the cloud-to-cloud resolution flawlessly. But what about the on-premises servers? I mean, they don't know about the VPC's internal .2 resolver. They sit all the way across the Direct Connect link. You can't just route on-prem traffic directly to a .2 address because those addresses are totally isolated within the VPC boundary.
And that is precisely the gap that Route 53 resolver endpoints were built to fill. In your shared services VPC, you deploy a Route 53 inbound resolver.
What does that actually look like? Am I basically deploying a managed server?
No, it's a managed endpoint. When you provision an inbound resolver, AWS drops elastic network interfaces into the subnets you specify across multiple availability zones. These ENIs receive private IP addresses from your shared services VPC.
Ah, so it's somewhat similar to the private link model. AWS provides the IP footprint, but manages the underlying compute transparently.
Exactly. You get highly available IP addresses that are routable over your Direct Connect. Then you simply log into your on-premises DNS server, whether that's Active Directory or Infoblocks, and you configure a conditional forwarding rule.
Making sense.
You basically tell the on-prem server, hey, if you receive any query ending in cloud.example.com, forward that query over the Direct Connect to these specific inbound resolver IP addresses.
And then the query hits the inbound resolver ENI, the managed service securely hands it off to the internal Route 53 engine, resolves the private hosted zone, and sends the answer back down the Direct Connect.
Total managed service. Highest possible performance because it's backed directly by the Route 53 control plane, and absolutely zero EC2 instances to patch, scale, or monitor.
I love it. We've laid the perfect private network plumbing, our traffic is locked down natively with private link, and our hybrid DNS is flawlessly routed without a single piece of legacy middleware.
The dream architecture.
Truly. But, a network is just empty pipes until you put workloads on it. So how do we architect the actual compute workloads sitting on these networks to scale cost effectively? Welcome to compute refactoring and the serverless cost equation.
This is where people get really passionate.
Oh, yeah. Let's look at a classic modernization scenario.
Yeah.
You are an architect tasked with refactoring a traditional monolithic web application that's currently running on a massive EC2 instance. The goal is to break it down into microservices. You have two environments to support, a production environment and a testing environment.
Standard setup.
Right. The traffic profile is crucial here, though. The load is highly variable. It spikes during business hours and drops near zero at night. But crucially, the minimum load and the absolute maximum peak load are known quantities.
Okay. Known bounds. That's important.
Yep. Your constraints are to design an architecture that minimizes operational complexity, and it must be the absolute most cost-effective solution for this specific traffic profile.
So whenever an exam question highlights minimize operational complexity alongside most cost-effective, you must ruthlessly evaluate the baseline idle costs of your proposed architecture. The idle tax is what absolutely destroys cloud budgets.
And here is where the community debate gets incredibly fierce. The hive mind argues passionately for container orchestration. They read the phrase, refactoring to microservices, and immediately shout, upload your images to ECR, run them on ECS or EKS with Fargate, and put them behind an application load balancer.
I say it every day.
When you push back on them, their justification is usually twofold. First, they claim you can't run a standard web app framework like Express or Spring Boot inside a Lambda function. And second, they complain that their container image is like 8 gigabytes, and they believe that's too big for a serverless function.
which is a perfect example of outdated information driving bad architectural decisions. Let's completely dismantle those technical misconceptions first.
Please do.
AWS updates its service capabilities constantly. The idea that Lambda only runs tiny snippets of Python code is a decade old. AWS Lambda natively supports deploying functions packaged as full container images. You can use your standard Docker tooling, build your image, and deploy it straight to Lambda.
And as for the size limit?
Lambda supports container images up to 10 gigabytes.
So if you have an 8 gigabyte container, Lambda doesn't even blink.
Right, it handles it fine. And regarding the web frameworks, tools like AWS Serverless Express or various language-specific adapters allow standard web applications to run seamlessly inside the Lambda execution environment. The API Gateway proxy integration handles the HTTP request translation perfectly.
Okay, but hold on. Let me play the skeptical FinOps engineer here. You're suggesting replacing an application load balancer with API Gateway and ECS with Lambda. Isn't API Gateway notoriously expensive at high scale? Like, if I have millions of requests, API Gateway charges per million requests. And ALB just charges a flat hourly rate plus some data processing fees. At a certain point, the math flips, right?
You are absolutely correct about the crossover point, but this requires a deep understanding of the specific constraints provided in the scenario. Yes, at a massive, sustained millions of requests per second scale, an ALB paired with ECS can become more cost-effective on a per-request basis than API Gateway.
Okay, so why not here?
Because we have to look closely at the constraints we were given. We have a variable workload that drops near zero at night. We have known minimums and maximums, meaning we don't need to over-provision for unknown hypergrowth. And crucially, we have two distinct environments, production and testing.
Right, let's run the math on the ALB side. If I use ECS or EKS, what am I actually paying for?
If you go the container orchestration route, you must deploy an application load balancer for the production environment and a completely separate ALB for the testing environment. ALBs carry a fixed hourly cost just to exist, 24/7, 365.
Just to sit there.
Exactly. They charge you whether 1 million requests go through them or 0 requests go through them. Furthermore, if you choose EKS, you are paying a flat hourly fee for the Kubernetes control plane for both environments. You are paying for Fargate tasks that might be sitting idle during low traffic periods unless you write highly aggressive and incredibly complex auto-scaling rules.
The idle tax.
Exactly, the idle tax. Now compare that to API Gateway and Lambda. What is the baseline cost of an API Gateway when there is no traffic? 0. What is the baseline cost of a Lambda function when it isn't executing? 0.
Wow.
For a variable workload where you want to explicitly minimize operational complexity, meaning no cluster management, no node groups, no auto-scaling rules to tune, no ALB target groups to manage, the serverless combination completely removes the idle baseline costs.
That makes total sense.
For dual environments with variable load, you pay precisely for what you use down to the millisecond. The serverless combination unequivocally wins the cost-effectiveness battle against managing dual ALB and container orchestration setups.
It's the purity of the consumption model. I love it. Now let's take serverless compute out of the region and push it to the absolute physical edge of the network.
Edge compute.
This next scenario trips up so many people because it requires a microscopic understanding of request routing. So here's the edge compute and legacy devices scenario. You are tasked with migrating an old on-premises metadata service to an AWS serverless architecture. This service is heavily accessed by older consumer devices. Think early generation smart TVs, legacy internet radios, older IoT hardware.
Stuff that hasn't been firmware updated in years.
Exactly. So the migration to the cloud goes fine, but you hit a massive roadblock during testing. Some of these older devices will literally crash and reboot if they receive certain modern HTTP headers in the response payload. They just can't parse them. Yeah. So your new architecture uses Amazon CloudFront at the edge, routing back to an application load balancer, which invokes a Lambda function to generate the dynamic metadata. Your objective is this. You must dynamically identify these legacy devices using the user agent header in the request and strip the unsupported modern headers out of the response payload before it hits the device.
Tricky.
And the debate in the forums is entirely focused on the compute execution location. Do we use CloudFront functions or do we use Lambda at edge?
This scenario requires a deep, deep understanding of the CloudFront request and response lifecycle. To solve this, you have to know exactly where in the data path you are allowed to intercept and modify the payload. There are 4 distinct integration points where you can inject compute in CloudFront: view a request, origin request, origin response, and viewer response.
Okay, let's unpack those 4 phases carefully.
There.
Phase 1 is the viewer request. This is the exact millisecond the user's smart TV hits the CloudFront edge location before CloudFront even checks its cache. Phase 2 is the origin request. CloudFront checked the cache, missed, and is now formulating the request to send back to the application load balancer. Phase 3 is the origin response. The ALB and backend Lambda have done their processing and are handing the data back to CloudFront.
Oh, then
And phase 4 is the viewer response. CloudFront has the final data, has cached it if applicable, and is just about to shoot it over the internet to the smart TV.
that is a perfect summary of the life cycle. Now, let's look at the compute tools available to us. CloudFront functions are incredibly lightweight, heavily sandboxed JavaScript functions that execute directly at the edge locations in less than a millisecond.
Super fast.
Super fast. But because they are so lightweight, they can only be triggered on viewer requests and viewer response events. They cannot make external network calls. They are designed for simple, high-volume tasks like cache key normalization, URL rewrites, or basic header manipulation.
Okay, and Lambda at edge.
Lambda at Edge, on the other hand, is a much more robust compute environment. It runs a full Node.js or Python runtime in a regional edge cache. It can be triggered on all 4 lifecycle events. It can make external network calls to third-party APIs, run heavier compute tasks, access the file system, and dynamically construct complex responses. The execution limits are much higher, up to 5 seconds for viewer events and 30 seconds for origin events.
Okay, wait, I'm looking at the requirements. We need to evaluate the user agent and strip a header from the response. That sounds like basic header manipulation. If CloudFront functions can modify headers on the viewer response, and they are significantly cheaper and execute faster than Lambda at Edge, why isn't CloudFront functions the answer? Why take on the deployment complexity of Lambda at Edge?
Because of where the problematic headers are being generated and the complexity of the dynamic evaluation required. The backend metadata service, the regional Lambda function sitting behind the ALB, is dynamically generating this response. It is constructing the payload and injecting these problematic modern headers based on its own internal logic. We need to strip these headers after the backend generates them, but before they are sent to the viewer.
Right, so we intercepted at the viewer response phase.
Yes. But here is the critical architectural nuance. The question specifies that we must evaluate the user agent to determine if we should strip the headers. If you use a CloudFront function on the viewer request, you can easily read the user agent. But you can't modify the response there because the response hasn't been generated yet.
Nice.
If you use a CloudFront function on the viewer response, you can easily modify the headers. However, depending on how caching is configured, complex logic that heavily modifies the response structure based on granular request attributes often pushes the limits of what a strictly sandboxed 1 millisecond execution environment can handle reliably, especially if the payload manipulation is intricate.
That makes sense.
But more importantly, let's look at the context of the exam's accepted patterns. The prompt explicitly notes that Lambda at Edge is the verified solution here. Why? Because Lambda at Edge gives you the robust execution environment needed to bridge complex state or logic between the request and response phases, or to manipulate the payload at the origin response phase before it even gets cached.
Oh, wait, if you strip the header at the origin response phase, CloudFront caches the clean version for that specific user agent, saving compute on subsequent requests.
Exactly. If you only manipulate the viewer response, you have to execute that compute for every single download, even on cache hits. By using Lambda at Edge at the origin response, you can evaluate the request context, strip the headers from the origin's payload, and allow CloudFront to cache that specific permutation. CloudFront functions simply cannot execute at the origin response phase. Only Lambda at Edge can.
Wow, that is the dividing line right there. You have to intercept the payload at the exact right moment in the lifecycle, and you need the compute engine that is actually authorized to operate at that specific moment.
Precisely.
All right, so we've got our compute layers scaling beautifully at the edge and in the region. We're highly available. But high availability is not the same thing as disaster recovery.
Not at all.
What happens when an entire AWS region takes a direct hit? Like an earthquake severs multiple transit lines or a massive routing anomaly isolates an entire geographic zone. Welcome to resiliency, failover, and disaster recovery. We really need to talk about active, passive failover strategies that mathematically satisfy the business constraints without bankrupting the company.
This is where architects earn their salaries.
Oh yeah. Let's start with a deceptive scenario regarding API and DynamoDB regional failover. You have an API gateway routing to a Lambda function, which reads and writes from an Amazon DynamoDB table. It is a beautiful, purely serverless stack. However, your compliance team mandates that this API must have the ability to survive a complete region failure. You need to implement cross-region failover.
Okay, standard DR requirement.
But the hive mind trap here is fascinating because it exposes a fundamental, persistent misunderstanding of how global DNS actually works. People go to the forums and say, oh, just deploy the stack in a second region, go to Route 53, and change the DNS record to a multi-value answer routing policy. Put both API gateway endpoints in the record.
This is the classic confusion between load balancing and disaster recovery. I mean, they are literally trying to use a hammer to turn a screw.
Break down exactly what multi-value routing does and why it fails this constraint so badly.
So multi-value routing in Route 53 is essentially a rudimentary form of client-side load balancing. When a user's browser queries Route 53 for your API's domain name, Route 53 looks at the multi-value record and returns up to 8 healthy IP addresses at random.
So it's like a smarter version of round-robin DNS.
Exactly. The client's operating system or browser then picks one of those IPs and connects. Yes, you can and should attach health checks to these records, so Route 53 stops returning the IP of a failed region. But think about the client-side caching behavior.
Right, the TTL.
DNS records have a time to live, or TTL. Even if Route 53 detects a failure and stops returning the bad IP, the user's local machine, their ISP, and their corporate firewall might cache that bad IP for minutes or even hours. Because multi-value is an active load balancing strategy at the DNS layer, you are constantly sending a portion of your user base to both regions.
Which is bad if one is down.
If one region hard fails, the clients holding that cache IP will experience hard errors until their local cache expires.
But our scenario is explicitly asking for a clean, active-passive failover capability. We don't want traffic in the secondary region unless the primary is absolutely dead.
Which is why multi-value is the wrong tool. If you want active-passive disaster recovery, you use a failover routing policy. You configure your primary region's API gateway as the primary record, and you attach a stringent Route 53 health check to it. You configure your secondary region's API gateway as the secondary record.
And then what happens normally?
Under normal operations, Route 53 only returns the IP for the primary region. 100% of your traffic goes there. The secondary region sits totally idle. The second that health check fails, Route 53 instantly pivots, and subsequent DNS queries are answered only with the secondary region's IP address.
Okay, that routes the compute gracefully. But what about the state? Like, what about the data layer? A failover is useless if the secondary API queries an empty database.
That's the other half of the puzzle. You convert the existing DynamoDB table into a DynamoDB global table. This is a fully managed active multi-region database. Under the hood, it leverages DynamoDB streams to asynchronously replicate every single write across your chosen regions, typically with sub-second latency.
What if there's a conflict during the failover?
If a write conflict occurs, say, 2 users update the exact same item in different regions simultaneously during a failover transition, DynamoDB uses a last writer wins reconciliation logic based on the timestamp.
So the complete, well-architected solution is deploy redundant API gateway and Lambda in region B, convert the data layer to DynamoDB global tables, and use a Route 53 failover routing policy tied to health checks. Clean, native, and perfectly decoupled.
Beautifully simple.
But let's turn the difficulty up. That was serverless. Serverless makes DR relatively easy because you only pay for compute when it runs. What happens when you are bound to legacy instance-based architectures? Let's look at the cost-constrained EC2 and RDS failover scenario.
Well, this one is absolutely brutal.
It really is. You have a multi-tier web application running on a fleet of EC2 instances behind an application load balancer. The state is stored in an Amazon RDS multi-AZ relational database. Your business has handed you a severe constraint. You must reduce your recovery time objective, your RTO, the absolute maximum time it takes to get the system back online after a regional failure, to less than 15 minutes.
15 minutes is tight for legacy instances.
Extremely tight. But T, the CFO, has explicitly stated you do not have the budget for an active multi-region strategy. You cannot afford to run a redundant fleet of EC2 instances idle in a second region just waiting for a disaster. You are heavily cost-constrained.
So we have to use a pilot light.
Exactly. Because you are on a budget, you set up a backup region using a pilot light strategy. You have an auto-scaling group in the secondary region, but the minimum capacity is set to 0. You also have an RDS cross-region read replica in the backup region, continuously syncing the data. So here is the puzzle. How do we detect a regional failure and orchestrate a complete failover, promoted the database, and scaling up the compute from 0 in under 15 minutes, completely automatically.
And this is where I see the most absurdly over-engineered Rube Goldberg machines in the forums. Seriously. People suggest creating complex CloudWatch metric math alarms. They want to monitor the primary ALB for 5xx HTTP error codes. If the 5xx errors spike for 5 consecutive minutes, the alarm triggers an SNS topic, which invokes a Lambda function, which then makes cross-region API calls to Route 53 to change the DNS records, and then makes more API calls to wake everything up. I'll be honest, as an engineer, writing that Lambda function sounds fun. Why shouldn't we do it?
Because it is incredibly brittle, and it fundamentally misunderstands how regional failures actually manifest in reality.
But so?
Well, relying on 5xx errors from a load balancer assumes that the load balancer is still reachable and functioning enough to even generate a 5xx error.
Right.
What if the region is experiencing a severe network partition? What if the internet gateway fails? The ALB won't return a 502. It will just silently drop the packets. The connection will time out. Your CloudWatch alarm looking for 5xx errors will literally never trigger, and your automated failover will never initiate.
Oh, wow. I didn't even think of that. Furthermore, if the region's control plane is degraded, those CloudWatch metrics might not even evaluate correctly or in time. You are relying on infrastructure inside the burning building to tell you that the building is on fire.
Okay, that is a terrifying visual. So we need an external observer.
Exactly. And that external observer is Route 53 health checks. These health checks do not run from within your VPC. They run from a global network of vantage points located all around the world. They constantly ping your primary ALB. They are native, they are incredibly fast at detecting failure, and they operate completely independently of the health of the specific AWS region your app is hosted in.
So walk me through the optimal native workflow that hits that sub-15-minute RTO without human intervention.
Step 1, you configure a Route 53 health check against your primary web application. You set it to a fast interval checking every 10 seconds. Step 2, you use a Route 53 failover routing policy. When that external health check detects consecutive failures from multiple global vantage points, Route 53 automatically, at the DNS layer, fails over the traffic to the secondary ALB.
But wait, Route 53 just sent the traffic to the secondary ALB, but the auto-scaling group behind it is at zero capacity. It's an empty load balancer. We need compute, and we need the database to accept writes.
That is step 3. You configure the exact same Route 53 health check status to trigger an Amazon CloudWatch alarm in the US East 1 region, where Route 53 metrics natively live, which in turn publishes a message to an Amazon SNS topic.
Okay.
That SNS topic instantly invokes a Lambda function that you have pre-deployed in the backup region. This automation Lambda function has 2 specific jobs. First, it makes an API call to RDS to promote the cross-region read replica. It breaks the replication link and turns it into a standalone primary database capable of accepting read and write traffic.
And is that a good job?
Second, it makes an API call to the EC2 auto-scaling service to update the minimum and desired capacity of the ASG from 0 to whatever baseline you need to handle the incoming traffic.
So the instances start booting up, registering with the ALB, and connecting to the newly promoted database. Going active multi-region is like keeping 2 identical cars running in your driveway 24/7, burning gas just in case the first one gets a flat tire. It's wildly expensive.
It really is.
Going active-passive with a pilot light and the ASG at 0 is like having a world-class pit crew on speed dial who promises they can build you a working engine in exactly 14 minutes. We are on a budget. We don't have gas money for 2 cars. We use the pit crew.
I love that analogy. And the pit crew in this architecture is the combination of Route 53 global health checks, SNS, and Lambda. It perfectly meets the sub-15-minute RTO constraint, and because the compute is scaled to 0 during normal operations, it costs a fraction of an active setup. You satisfied both the resiliency and the financial constraints perfectly.
Let's look at one more resiliency scenario before we move on to governance. This one is about graceful degradation and custom errors. It's a classic incident response puzzle. You are the architect managing an ALB that sits behind an Amazon CloudFront distribution. Suddenly, your monitoring dashboards light up. The ALB is occasionally returning a 502 bad gateway error.
Okay, 502s are never fun.
You investigate and find that a recent application deployment introduced a subtle bug where malformed HTTP headers are intermittently returned to the ALB. The ALB can't parse them, so it throws a 502. But here's the kicker. It's intermittent. If the user just hits reload in their browser, the next request usually hits a different container and returns successfully.
Frustrating for the user, but manageable.
Right. The dev team has identified the bug and is actively working on a hotfix. But in the meantime, as the architect, you have a directive from the product team. You must provide a branded custom error page to the users instead of the ugly default ALB 502 error page.
Makes sense.
The constraint is you must implement this custom error page with the absolute least operational overhead and minimum risk to the routing layer.
This is a textbook graceful degradation scenario. You have an active incident. The system is bleeding. You need to apply a Band-Aid that improves the user experience without causing more trauma to the system.
Exactly. And the distractor I see proposed for this is genuinely terrifying. People suggest using CloudWatch alarms to detect the 502 errors. When the alarm trips, it triggers a Lambda function. That Lambda function then makes an API call to the application load balancer to dynamically modify the core forwarding rules, injecting a new rule that points traffic away from the application target group and towards a different public web server hosting a static error page.
Oh, absolutely not.
I'm an infrastructure guy, and the thought of an automated script altering production ALB listener rules during an active incident makes my blood run cold.
It absolutely should. It violates every principle of safe incident management. During an ongoing production outage, the absolute last thing you want to do is introduce dynamic, automated mutations to your core routing layer.
It just adds so much risk.
Think about the failure modes of that proposed solution. What if the Lambda function times out? What if it modifies the wrong listener rule? What if the alarm flaps, turning the rule on and off every 60 seconds as the 502s spike and dip? You're introducing massive operational risk. You could turn a partial degradation into a complete hard outage.
So how do we gracefully decouple this? How do we serve the error page without touching the ALB?
You handle edge errors at the edge. The scenario explicitly mentions that Amazon CloudFront is already configured in front of the ALB. That is your decoupling layer. The elegant, lowest risk solution is to host a simple static HTML file, your branded custom error page, in a standard Amazon S3 bucket. Then you go to your CloudFront distribution settings and configure a custom error response.
Oh, just a native feature.
Yeah. You simply tell CloudFront, if the origin, the ALB, returns an HTTP 502 status code, do not pass that 502 back to the user's browser. Instead, silently fetch this specific static HTML page from this S3 bucket and return it to the user. You can even configure CloudFront to change the HTTP response code it returns to the viewer, like changing the 502 to a 200 OK or a custom 503, depending on how your client applications handle retries.
It's brilliant because it completely bypasses the application routing logic.
Yeah.
The application backend is struggling, so you intercept and mask the failure at the content delivery network layer. You don't touch the backend ALB rules at all. You just let the developers fix a header bug.
Right.
Once they deploy the hotfix and the ALB stops throwing 502s, CloudFront naturally stops serving the S3 error page. The system heals itself without a single routing change.
This raises a critical evaluation metric for anyone taking the SAP-C02. Are you solving the problem at the right layer of the OSI model or the right layer of the AWS global infrastructure? Always look for the decoupling opportunity. Never introduce stateful routing changes to solve stateless application errors if you can avoid it.
That's a great rule of thumb. Okay, we are moving into the final phase of our architecture build. We have the network, we have the serverless compute, we have the active-passive failover. But as a senior architect, for you out there listening, you aren't just managing one app. You are managing dozens, maybe hundreds of AWS accounts across a massive enterprise. You are responsible for security guardrails, compliance, and multi-million-dollar cloud migrations.
It's a whole different scale.
Welcome to enterprise governance and automated migrations. Let's start with a nasty IAM logic puzzle that trips up almost everyone the first time they see it. This is the service control policy logic trap. Here is the scenario. Your enterprise uses AWS organizations to manage 100 different AWS accounts. You have a very strict compliance posture. At the very root of your organization, you have attached a service control policy, or SCP, that acts as a deny list.
Okay, root level deny.
It explicitly denies access to unapproved AWS services. Let's say it explicitly denies any actions against AWS config, because central IT strictly manages config rules via CloudFormation stack sets. Now, your company acquires a new startup. You invite their existing AWS account into your organization. To keep things organized, you place their account into a newly created organizational unit called the Onboarding OU.
So they are sitting right under the root.
Right. Immediately, the startup's engineers open a critical ticket. They need to update their local AWS config rules to bring their infrastructure into compliance with your corporate standards. But every time they try, they get an access denied error. Why? Because that root level deny SCP is cascading down and blocking them.
Naturally.
Your goal is this. You must allow the new onboarding OU to make changes to AWS config so they can remediate their infrastructure. However, you must continue to enforce the strict deny policy on the rest of the company. And you must accomplish this without introducing long-term maintenance overhead, like managing complex IAM condition keys for every single user.
Service control policies are the ultimate immutable guardrails of an AWS environment, but their evaluation logic is counterintuitive if you are used to standard firewall rules.
I see this constantly on the forums. The hive mind looks at this problem and says, that's easy. Just create a new SCP that has an explicit allow for config star actions. Attach that new allow SCP directly to the onboarding OU. The allow will override the deny for that specific OU. Done. Why is that fundamentally mathematically incorrect?
Because it completely violates the AWS IAM policy evaluation engine mechanics. In AWS IAM, an explicit deny trumps absolutely everything. It does not matter how many explicit denies you stack up underneath it. It doesn't matter if the user has full administrator access. If an SCP at the root of the organization says deny action X, that deny cascades down the entire inheritance tree through every organizational unit, every child OU, every AWS account, every IAM role, and every IAM user.
It's absolute.
It is absolute. You cannot override a higher level deny with a lower level allow. The evaluation engine stops the exact moment it hits the explicit deny.
So the onboarding OU is essentially trapped under a concrete ceiling. The root deny is crushing them. How do we free them without removing the protection from the 99 other accounts? I could write a complex condition key using AWS principal origd to exclude them, but the prompt says avoid long-term maintenance overhead. Condition keys get messy fast.
You don't fight the policy evaluation engine, you alter the architectural inheritance tree.
Walk me through that.
You do not touch the onboarding OU's policies. Instead, you go up to the organization root, you take that restrictive deny SCP, and you physically detach it from the root. You then attach that exact same deny SCP directly to the production OU, which is the organizational bucket that houses all your existing corporate accounts.
Oh, I see. You are shifting the enforcement boundary.
Precisely. By moving the deny policy down one level in the hierarchy into the production OU, you maintain the exact same impenetrable security posture for the legacy company. But look at the onboarding OU. It is a sibling to the production OU. It sits adjacent to it, directly under the root. Because the deny policy is no longer attached to the root, it no longer cascades over the onboarding OU.
That's brilliant.
The startup's account is freed from the restriction entirely by virtue of topological placement, not by trying to fight a deny with an allow.
That is such a critical distinction. If you are preparing for the SAP-C02, burn this into your brain. An explicit deny at a higher level cannot be overridden by an allow at a lower level. Understanding the topology of policy evaluation is the dividing line between a mid-level engineer who writes messy condition keys and a professional architect who leverages structural inheritance.
It's all about structure.
All right, let's pivot to a different kind of enterprise challenge. Migration governance. Here is the scenario. Your CIO has decided to exit your on-premises data centers entirely. You are tasked with migrating thousands of VMware virtual machines to AWS. But before you are allowed to migrate a single byte of data, the CFO slams the brakes.
They always do.
They demand a comprehensive total cost of ownership report and a massive financial business case to justify the cloud spend to the board of directors. You look at the AWS migration toolset, and the forums are arguing endlessly over which tool to deploy to gather this data. Half the people say use AWS Application Discovery Service, and the other half say use Migration Evaluator.
This is a classic exam vocabulary trap. AWS has a massive portfolio of migration tools, and they sound very similar. Both of these tools are utilized in the early stages of a large-scale migration, but they serve entirely different masters. One serves the engineers, the other serves the accountants.
Let's set the record straight so nobody gets this wrong. What is the precise architectural difference?
Let's start with AWS Application Discovery Service, or ADS. ADS is a deep dive technical dependency mapping tool. You install its agents on your on-premises servers, or you deploy its agentless collector in your VMware vCenter.
And what is it looking for?
ADS sits there and meticulously watches the network traffic. It figures out that web server A talks to database B on TCP port 1433 exactly 400 times an hour. It builds complex dependency graphs. You use ADS when you, the architect, are trying to figure out which servers need to be grouped together into migration waves. If you move the web server to the cloud but leave the database on premises, the latency will break the application. ADS prevents that by mapping the technical dependencies.
But ADS doesn't spit out a financial prospectus for the CFO. It just tells me what talks to what.
Exactly. If the scenario prompt mentions business case, financial forecast, total cost of ownership, or TCO, You must immediately discard ADS and select Migration Evaluator.
Okay, what does Migration Evaluator actually do?
Migration Evaluator, which used to be an acquisition called TSO Logic, is a specialized financial modeling engine. It is explicitly built to ingest bulk data from your existing Configuration Management Database, or CMDB. It analyzes historical CPU, memory, and disk utilization metrics.
Ah, so it's looking at usage.
Right. It then runs a right-sizing algorithm and outputs a highly detailed financial business case. It will literally generate a report that says, based on your actual historical utilization, if you move these 1,000 on-premises VMs to these highly specific right-sized EC2 instance types and purchase these specific compute savings plans, your projected monthly AWS bill will be exactly this much.
So it's basically a strict keyword association game for the exam, but it's rooted in actual migration phases. If I see financial modeling, TCO, or business case.
You select Migration Evaluator. If you see network dependencies, TCP connections, or migration waves, you select Application Discovery Service.
Crystal clear. Let's finish up with our final enterprise governance scenario. This one is a massive headache for FinOps teams everywhere. Topic C is enforcing compliance cost-effectively. You have a large organization with hundreds of developers building applications across dozens of AWS accounts. These applications frequently pull massive amounts of data from Amazon S3. We are talking petabytes of machine learning training data.
Oh, that's going to get expensive.
Because the developers are prioritizing speed and agility, they're just deploying standard default VPCs. They drop their EC2 instances in private subnets, route the outbound traffic to a NAT gateway, and pull the S3 data over the public internet. Suddenly, your monthly AWS bill arrives, and the CFO is screaming. You have racked up tens of thousands of dollars in pure NAT gateway data processing charges just to pull data from S3, which is an AWS service.
It happens all the time.
The Central IT Board issues a mandate. You must proactively enforce that developers only deploy approved VPC architectures. Specifically, every single VPC must have an S3 gateway endpoint baked into the routing tables, which ensures S3 traffic stays on the free AWS backbone and bypasses the expensive NAT gateway.
Makes perfect sense.
But here's your constraint. You absolutely cannot slow the developers down. You cannot force them to submit IT tickets to provision VPCs. They must retain self-service capabilities.
This is the eternal struggle of cloud architecture, agility versus governance. How do you force people to eat their vegetables without closing the buffet?
I love that. The Hive line usually leans toward reactive governance here. They suggest deploying AWS config rules. They say, write a custom AWS config rule that constantly scans the accounts. If it detects a VPC without an S3 gateway endpoint, configure an automated systems manager remediation document that terminates the EC2 instances inside that non-compliant VPC.
Ooh.
I despise this approach. As a developer, if I spend 2 hours deploying a complex machine learning stack, start a training run, and suddenly an automated script swoops in and terminates my instances because I missed a compliance check on a route table, I am going to lose my mind. You have completely destroyed their productivity.
You are exactly right. That is a hostile reactive architecture. It punishes the developer after the fact and creates massive friction between engineering and security.
Okay, so what if I just write a pristine, perfect CloudFormation template for the VPC, email it to all the developers, and say, please only use this template to build your networks?
Well, it's a step in the right direction, but how do you mathematically enforce it? If the developers possess full IAM permissions to call EC2 create VPC or EC2 create route table, they can just ignore your email, log into the AWS console, and build it manually anyway. You have provided a suggestion, not a guardrail.
So how do we solve this? How do we proactively enforce the perfect architecture, prevent the NAT gateway billing bleed, and still let developers provision resources instantly on their own?
You implement AWS Service Catalog. This is the ultimate proactive governance tool.
How does the workflow actually play out?
Here is the workflow. You, as the central architect, author a pristine, well-architected CloudFormation template. This template deploys the VPC, configures the private subnets, provisions the NAT gateway for external internet access, and crucially, deploys the S3 gateway endpoint and updates the route tables to prioritize it. You take that perfect template and you package it as a product inside an AWS Service Catalog portfolio. You then share that portfolio across your entire AWS organization.
Okay, but how do I stop them from just bypassing the catalog?
You change their IAM permissions. You revoke the developer's raw ability to call EC2 create VPC. You strip away their underlying infrastructure permissions. Instead, you grant them IAM permissions only to execute products from the AWS Service Catalog. Furthermore, you apply a launch constraint to the Service Catalog product. The launch constraint tells the service catalog to assume a highly privileged IAM role behind the scenes when deploying the template.
Oh, that is incredibly slick.
It satisfies every constraint perfectly. The developers still get self-service infrastructure. They log into the AWS console, navigate to Service Catalog, see the approved enterprise VPC product, and click Launch. It deploys in minutes. They aren't slowed down by IT tickets or manual approvals, but because they can only deploy what is in the catalog, you as the architect have an absolute mathematical guarantee that every single VPC provisioned in the enterprise has that cost-saving S3 gateway endpoint correctly configured in the routing table.
You completely eliminate the NAT gateway data transfer cost proactively. You eliminate the risk of human error in routing configuration, and the developers still feel like they are moving at the speed of the cloud. That is what a professional-level architectural solution looks like.
It's governance at scale.
All right, we've covered an immense amount of ground today. We started with the deep mechanics of VPC sharing via RAM and securely consuming third-party APIs using the hyperplane architecture of Private Link. We modernized hybrid DNS by ditching legacy EC2 forwarders for native Route 53 resolvers.
You moved a lot of traffic.
We did. We completely refactored compute architectures, proving how API Gateway and Lambda mathematically defeat container orchestration idle taxes for variable workloads. We intercepted legacy payloads at the edge using Lambda at edge origin responses.
Save those old smart TVs.
We survived regional disasters on a shoestring budget using pilot-light auto-scaling groups triggered by global Route 53 health checks. And we gracefully degraded our applications using S3 and CloudFront to bypass failing load balancers. And finally, we wrangled massive enterprise governance, shifting SCP inheritance topologies, accurately modeling TCO with Migration Evaluator, and enforcing proactive FinOps routing using AWS Service Catalog.
If there is a unifying principle to all these complex scenarios, it is this. Passing the SAP-C02 isn't about simply knowing what a single AWS service does in isolation. It is about understanding the underlying mechanics of those services well enough to evaluate brutal constraints, cost, RTO, scaling limits, and operational overhead, and systematically avoiding the trap of doing things the hard legacy way just because it feels familiar.
The hive mind will always try to push you toward building a massive transit highway when a simple shared bedroom key will do. They will push you toward active multi-region server fleets when a pit crew on speed dial is mathematically sufficient to meet the RTO.
And that raises a final vital perspective for you to consider as you continue preparing for this certification, and more importantly, as you design systems in the real world.
Exactly. I want to leave you, the listener, with a challenge. The next time you are standing at a whiteboard sketching out a new architecture, I want you to step back and ask yourself a hard question. Am I building this complex system because it looks impressive to my peers? Am I deploying container orchestrators and dynamic routing automation because it's technically thrilling? Or am I building this because it cleanly and mathematically satisfies the actual business constraints I was given?
It's a tough question to answer, honestly.
It really is. The true test of a solutions architect isn't just surviving a disaster when the servers go down. The true test is realizing that a high-maintenance, over-engineered architecture is itself a disaster waiting to happen. Clear the mud. Find the elegant native abstraction. Keep diving deep, trust the constraints, and good luck on the SAP-C02.